All right, guys, we're in the final stretch. We are going to take a look at chapter 22. Now, you want to pay attention as we go along because we're not going to do all of chapter 22. We're going to do nomenclature. We're going to review a little bit of preparation reactions, and we're going to learn a few new ones. And so let's just jump right in. So just to review, hopefully we all know the functional group amines by now. There's a nitrogen attached to a carbon, and then potentially, two or one or no hydrogens. A primary versus secondary versus tertiary amine is a little bit different than when we talk about alcohols or carbocations. We are actually talking about what's attached to the amine and not to the nearest carbon. So everything is kind of a derivative of ammonia. A primary amine has one R group, secondary has two, tertiary has three. There's plenty of naturally occurring amines. If you've ever heard the term alkaloid, that is referring to an amine. There's amines present, as you can see here, in a wide variety of drugs. Just like any functional group in this book, they're present in all sorts of areas. So here's another example of some biologically important neuromolecules. Now, amines, we have seen since Organic 1 act as a base, act as a nucleophile. You got a nice SN2 reaction here, simply just acting as a base on this side. We've got that lone pair, so you have a lot of electron density right there. That is great for different kinds of reactions. As we talk about nomenclature, so our final foray into nomenclature. Amines are not too bad. If you've already learned how to name amides, these are, it's not too much extra. There are two different ways you can name them, though. One that's pretty simple, and then the other one that's more useful if you have sort of complex naming. And so we're going to start off here with some primary amines. And we're going to start off with our first option. Our first option is going to just it's kind of like the common way you can name alcohols, where ethanol is ethyl alcohol. It looks like that format, but it's just IUPAC approved. And so it's fairly easy. Whatever your R group is your alkyl. And then if you have an NH2, it's just amine. All right, so you have examples over here: ethylamine, isopropylamine, cyclohexylamine, right? So you can use if there's easy common names, cyclic structures work well. But you could see how that could be difficult if you had something like this, where there's not just an easy way to name it. So our second way is good for more complex structures. And the way that you're going to handle that is you're going to treat it more like other functional groups. You're going to drop the E from the parent, and you're going to add amine. Right? So you could even do that with some of these easier ones, right? So this right here is ethyl amine. But you could name it with the more complex naming scheme, and this would be ethanamine. Right, so this one works for everybody. It's just you really have to go with this second structure when you have something more complicated. All right, so let's go through this naming here. You want to give the lowest numbering to the amine possible. And hopefully by now you've picked up on this. Whatever functional group is giving you that suffix, is giving you the parent name, that's the high priority, right? And the high priority is going to also have priority when it comes to numbering. So you only go to other substituents if it doesn't matter. Like if this amine was on the 4 position, then you might choose one of the other substituents. And if they're at the very end, you can use alphabet to break ties. But in this case, we want to go from left to right because the amine, that puts the amine on 2 instead of 6. So then we have 2 chiral centers with stereochemistry. So you're still going to be expected to use R and S when appropriate. And so we see that we have a 2R, 4R, 4,6-dimethyl, and you have to put the location of the amine, right? 2-heptanamine, or you could do heptan, let's let that go away, heptan 2-amine, just like you've done with other functional groups. Now you'll notice I didn't put a number over here in ethanamine because ethanamine is going to be 1 ethanamine no matter what you do. But you could, of course, put it in there if that makes you feel better, if you like to be consistent. Before we go on, we would see the same thing if we had, let's say, a double bond, and then maybe we'll have even a chiral center here. Why not? Let's play with that. In this case, right, now, whichever way we number would give the amine on carbon 3. Amines are higher priority than alkenes, but since it's 3 either way, we'll go for the lower numbering for the double bond next. Right, it's kind of our tiebreaker. So this is a pentene, so this becomes pentenamine. Now, you'll see me put the numbering inside the name. You see me do that anytime we have like an E9 or an enol or an ene and another functional group. We don't have E and Z because there's 2 hydrogens here, so there's no stereoisomers there, but we do have our R and S issue. So we know that the nitrogen is number 1, the carbon in the double bond is number 2, and the CH2 is number 3, hydrogens to the back. This is an S chiral center. So this becomes S, pent, 1 ene, 3 amine. Gives you everything you need to know there. Now, amines aren't always highest priority. You will have that priority list when you take your exam 4 and your final. And if the amine isn't the highest priority functional group or in the structure, then as a substituent, it's called amino. I'm sure we've used it before at this point, but just reviewing it here. So alcohol's higher priority. This is for aminobutanol, right? It's definitely not the highest priority. Carboxylic acids are at the top, so we have para-aminobenzoic acid. That is definitely something you should know. We've already done the nomenclature of aromatic amines, and that's aniline. So this right here is just a review from previous chapters. To finish this up, we want to talk about what has to change or what happens if you have secondary and tertiary amines. Now, there's still 2 methods, right? There's the first method that works if everything is simple. You're going to use Greek prefixes here. You're going to use alphabetization. You're going to use the alphabet to organize. Alphabetize. There we go. So, for instance, let's look right here. There's 3 methyl groups. That's trimethylamine. 2 ethyl groups, diethylamine. If you have different simple groups, you just write them all down in alphabetical order. Ethyl, methyl, propyl, amine. All right, it's very simple, but you can see again, this only works if all of those groups are pretty simple. Right, second option, we're dealing with more complexity. it's going to look a lot like our second option previously, but now it's going to add in something you saw when we dealt with amides. Now, I am not going to give you something, an amine that has more than one complex group. At some point, we have to say that's enough nomenclature rules, and so that's where we call it here. So, substituents on the nitrogen, right, that aren't going to be part of your parent, are going to have a locant of N, right? Just like we saw with amides. You could use this even on a simple structure. So for instance, let's say we had, where did they put that? We had this ethyl group. There was a propyl group and a methyl. You could still use that here. You would choose the longest continuous chain. And this would be N ethyl, N methyl, 1 propanamine. That would work. You could also see why it might just be easier to just say ethyl methyl propylamine, but this follows all the rules. It's even better, you know, or more necessary when you have something big and complex like this, when you've got some chirality you need to deal with, right? So in this case, we want to count our parent chain to give the lowest numbering possible to what makes the parent name. So this is going to be an S, right? So 1, 2, 3, hydrogen to the back, 1, 2, 3, counterclockwise, S. There's 2 chlorines on carbon 2. There's an ethyl and a methyl group on N, right? So N's N's are locants here. And then 3, hexanamine. Let us know where that amine is located on the parent chain. Now, what about if you have multiple substituents? So I'm going to try and do something sort of easy here. Let's say we have just a whole bunch of methyl groups. And then we'll put an ethyl group here for fun. Our parent is going to be 1, 2, 3, 4, 5, 6. So we have a 3-hexanamine as our parent. And then we've got 1, 2, 3, 4 methyl groups and an ethyl group. So ethyl comes first. So we're going to do N-ethyl. But then I'm still going to add up all my methyls and put them together. And they are going to be at 2, 4, 5, N, tetramethyl, 3-hexanamine, right? I think that's it. Yeah, and that is all of our nomenclature. So before we get to reactions, we'll talk a little bit about properties of amines here. Nothing new or surprising. Some sp3 hybridization. That gets more complicated with aromaticity, as we saw. And that's, I think, what they're getting to right here. What circumstances would the nitrogen be sp2 hybridized if it could be aromatic? There are nitrogen atoms that can be chiral, but typically they're not optically active. So we're not going to worry about that. When it comes to properties, we, as expected, because of hydrogen bonding, we see an increase in boiling point from something with only CHs, but it's not nearly as big as the OH, because while they can both hydrogen bond, oxygen's more electronegative, so the proton is even more exposed. The more R groups you add, right, you see that trend going down. It's because this guy has 2 hydrogens that can hydrogen bond. This one only has 1. This one has done. Now, amines are something that if you ever work with them, you don't forget, because they tend to have a pretty fishy or unpleasant odor. if the names of these two don't tell you everything you need to know, I don't know what to tell you. Putrescine and cadaverine, both amines, don't smell very good. Amines, as we have discussed, are fairly basic. They're stronger bases than alcohols and ethers, but they're weak bases in comparison to like a hydroxide. We've already done all our acid and base talk, so we're going to keep going. If you took Organic 1 at Blend, you did this already. Amines are really interesting. They tend, if they're part of a large organic structure, they tend to be soluble in organics. And so if you need to get an amine away from other things that are in the organic layer, you can add acid. You would make this amine salt, and then this might be more soluble in water, right? Because it's a salt. More soluble in water. In fact, you might be familiar with this already. There is a technique for making drugs that aren't particularly soluble in water more bioavailable by mixing them with an acid. So if you've ever taken a drug that was, drug name, hydrochloride, that's why that hydrochloric acid is there. The hydrochloride is really not in HCl form. It's in this amine Cl- form that is going to be more soluble in water, therefore more able to get to where it needs to go in your body. So that it can be helpful for extractions. It can be helpful practically with pharmaceuticals. Arylamines are less basic. Again, this all goes back to like chapter 3, talking about acids and bases and then resonance. We're not going to spend a lot of time there. Amines have fairly different properties from amides because this resonance really takes a lot of that electron density off of the nitrogen, and it shares it more with that oxygen, so it's not nearly as basic or nucleophilic. They're pretty stable. We absolutely are not going to calculate pHs and pKa.